Hello everyone and welcome to FatalSec. To showcase some of the exciting FREDA detection techniques, I have developed a sample application which is already installed on my mobile device, and it's a very simple application in terms of UI. We have three different labels saying FREDA detection 1, 2 and 3 along with the status mark where if FREDA is being detected it shows a red cross icon, otherwise it will display this green tick mark. So our goal here is to reverse this app to understand the logic which is responsible for these detections and create a FREDA script to bypass all these checks. Let's start the analysis. So I have the APK file present in this directory on my machine. Let's open the terminal here, and to analyze this application, we are going to use JADX tool to see the decompiled code and understand the code present in this application at Java layer. So as you can see here, we have this app release.apk, and I have JADX GUI already configured in my environment variable. So just by typing JADX GUI, it will launch this tool. Okay, open file, select app release.apk, open. Once the decompilation is done, we get this nice looking interface where on the right hand side we can see all the packages present in this application. So most of the package names are stripped out as we are only getting package names in the form of characters followed by a number such as B0, B1, C0, right? So as you might already know that all Android application components such as activities, services are defined in a file called Android manifest.xml. So let's directly jump into that file which is present in under the resources directory, Android manifest.xml. Let me try to increase the font size a little bit. Okay, so in the manifest we can see that there are a few components defined. First one is the activity which contains main activity, and since there are no other interesting component defined here, this becomes the only point of interest for us as of now. So in order to see the decompile code for this activity, either we can directly double click this class from here, or we can find the package name where this main activity class is present, which is mentioned right here, that is com.fatalsec.antifrida. Again, on the right side in the navigation pane, we can find out this package here. It's com then fatalsec.antifrida, and if we expand it we will get this main activity, right? Okay, so the very first thing we can observe in this class is that it has some kind of obfuscation, as we can see some of these random characters being printed here, and also JADX GUI tool is not able to decompile this on create method where the whole UI logic is usually defined. But still we can make note of some interesting things from here, such as in the static block it is trying to load a native library via system.loadLibrary API, and the name of the library is antifrida. And then we can see three native exported functions named detectfrida1, detectfrida3 and detectfrida2. By the name of these functions, we can assume that these are the three functions defined in this native library, which are responsible for all the FRIDA detections present in the application. Right, and as we already checked from the manifest, there are no other activities or classes defined. The only thing left for us to analyze is this native library, which is antifrida. Now, usually all the native libraries we can easily find under resources lib. Then here you will find different architectures for which the library is built. In this case, I have only built this application for ARM 64-bit CPUs, and if we expand this one we will get this libantifrida.so native library, right? Next, in order to analyze this native library, we first have to extract it so that later we can analyze it into a disassembler, right? So there are a couple of ways in which we can extract this library from the APK, such as by using APK tool. Another one is just by renaming the APK file with the zip extension and then unzip it using any unzip utility tool. And the third way which I'm going to use is simply by saving the output of this JADX tool. So here on the top menu bar it says save all. I am going to save it under antifrida directory, save, and here down below you can see that it's saving the resources. Give it some time. Alright, so the output is saved now. And if we go back to the directory, we see that two new folders are created, resources and sources. So the sources directory will contain all the decompiled classes, okay, and the resources directory will contain the resources part of the application, such as the manifest, file, assets, library, right? So as we just saw in the JADX tool, that under library architecture we have this libantifrida.so library present. So in order to analyze this native library, this time I am going to use Radare 2 disassembler as well as Ghidra. You can of course use any other disassembler such as IDA, but there is a specific reason why I am using Radare 2 and you will find it very soon. So let's open a new terminal over here. Okay. To load the library into Radare 2, we can simply type this command R2 followed by the name of the library we want to analyze, which is libantifrida.so in this case. Then we have to tell Radare to perform the analysis by using 6 times a command. This will perform an in-depth analysis, and once the analysis is done, we can get a list of all the functions using afl command. Alright, so this lists out all the functions present in this library. Here we can obviously see those exported functions: detect frida 2, detect frida 3 and detect frida 1, right? As this is a sample application, we are able to see these function names clearly. Otherwise, when you try to analyze a real world application, it may not be so obvious. So let's analyze this binary the same way. Instead of analyzing these functions, we will try to analyze the binary as if these functions are not there. For that, instead of listing out all the functions, let's list only the imported functions. So to list out all the imported functions, we have I command, and there we have all the imported functions listed out by this Radare tool. Pthread create, pthread join, scanf, random, string length, malloc, connect, socket. All these functions are coming from libc library. Libc.so is a shared library in Android that provides fundamental functionality to C or C++ programs running on the system. And this library contains pretty much all these functions which are listed here. Since it's a small library and contains very limited number of imported functions, we can directly try to hook all of them and try to intercept these functions. But I am only going to hook those functions which are responsible for Frida detection. So the functions which looks quite interesting to me are connect and socket functions, because this is a sample application which is not making any connection to the outside world. So what's the need of creating this socket, right? All right, so let's open VS Code. Let's name it as script.js. We are straight away going to intercept this connect function. So for that, let's write the interceptor to replace the overall implementation of this connect function. We are going to replace the implementation of this function because later on you will realize that we have to modify some of the arguments of this function in order to manipulate its return value. So with native functions, it's always better to replace the overall implementation instead of just intercepting the function. So for that, we have interceptor dot replace API. All right, and this takes two argument. First one is the address of the function. In this case, this function is going to be our connect function. So let's create a connect pointer variable which will contain the address of this connect function. And to figure out what's the address, we have module dot find export by name API. Here first we have to tell under which library this function is present. So as we know, it's coming from libc.so. Then the name of the function, which is connect, right? So this is going to be the first argument of this function. Then the second argument is going to be the callback function, which will be triggered whenever this connect function is going to be called. So for that, we have new native callback. Here we have to define the arguments of the function. And if you don't know what this connect function looks like and what are the arguments of this function is going to be. What you can do is simply type connect and look into its Linux manual. So here we have the manual page, and as you can see, this is the signature of this function where integer is the return type. So it will return either 0 or 1 based on the status of the connection, and it's taking a socket file descriptor, then a socket address, and then the length of the socket address. So we have to match this signature. So first one is going to be the file descriptor, second one is going to be the address, and third one is going to be the length. All right. Okay, now to identify what is the structure of this socket address, what we can do is again simply Google this structure. There again we have this Linux manual page where we can see the structure of socket address. In this structure, the first field is SA_family. This field specifies the address family of the socket. What it means is if you want to use IPv4 address, then pass AF_INET in this family, or if you want to use IPv6 address, then you have to pass AF_INET6. Then the second field is SA_data. This field is an array of characters that contains the actual socket address, and in this field only the port number is defined where the connection or where the socket is going to bind. Okay, so how can we extract these fields from a structure in our Frida script? Now we know that the second field is the socket address where the port is actually present in a packed format, and we can extract this port from this socket address field by performing some bitwise operation and shifting, which we will see later. So the first field we are going to extract simply by using addr dot read u16. Why I have used read u16? That's because this SA family underscore t, it's an unsigned integer type. Okay, let's store this into family variable. Then we have to extract the port. So in order to extract the port, it's a second field, which means we have to move ahead to the second field in this structure, right? Here this address variable is containing the address of this structure, which is pointing to the first field. So in order to point to the next field, we have to increment this address by certain value. And since this field is of unsigned integer type, the second field is going to be present 2 bytes ahead, right? So to get the second field, what we can do is we can add 2 to the address, and now we are pointing to this field instead of the first one. And now let's read this value using read u16 again. But if you now try to print the port, you will get some random integer number because, like I mentioned, the port is present in a packed format. So there is a standard way to unpack it by performing an AND operation with FF. This operation extracts the least significant byte of the port variable. Then we will perform left shift. This operation shifts the least significant byte of port to the left by 8 bits. Then we will perform a right shift operation by 8. This operation shifts the entire port variable to the right by 8, which effectively discards the least significant byte of the port. And then finally, using this pipe symbol, we will combine the results of these two steps. So this is the magic operation using which we will get the port in a human readable format. Now let's print this port using console.log connect, print this port, and in the end we have to return the connection, right? So for that we have to call connect function with the original arguments, so that whatever the connect function is returning in the first place, our custom function is going to do the same. So for that, let's make the original connect function using native function. This will take connect pointer followed by the return type of the connect function, which we know is integer, and then the arguments of connect function. So the first argument of connect function is of type integer, then the second argument is socket address of type pointer, right? So this is going to be pointer, then the third argument is of type integer again. So now we can simply call this connect function and pass our original arguments, ft address and length, which we have mentioned here. Let's save the script. And in order to test this Frida script, we have to first start the Frida server on our device. But before that, I would like you to make a note that as of now, when the device is in clean state, we are getting these green tick marks in all of the detections, right? So let's now jump back to the terminal and go to ADB shell, taking the root permission, going to data local temp directory where my Frida server is present, and let's run the server. Okay, and if I launch the application again, there are chances that certain detections may have triggered this time. So if I launch the application again manually without Frida, I mean only the Frida server is running, and this time we are getting only one green tick. The other two detections are triggered. Okay, now let's try to test this script. For that, I am going to open a new terminal in this VS Code itself. Okay, and to launch the script, we have this command frida-u, which tells that our device is connected via USB, followed by -l, and then the name of the script, then -f to forcefully spawn a new instance of the application on the device. And this expects the package name of the application, which is com.fatalsec.antifrida, right? Enter. And it says missing argument script.js line number 9. Okay, what's wrong here? Replace pointer is defined, native callback is, oh, okay. Here we also have to tell what is the return type of this function, which is integer, and then the arguments of the function, which is integer, then pointer, then the third argument is of type integer again. Clear and launch the script again. As we see now, this time all the detections are triggered. So in the console we can see that this connect function is being called 3 times. The first 2 times it tried to connect to port 12132, and then third time it's trying to connect to 27042. Now to better understand this, prepared a small presentation where I tried to explain all the techniques used in this application using some block diagrams. But before moving forward, if you are not interested in the theory part, feel free to skip this section and also drop a comment if you prefer explaining solely based on the analysis part followed by a Frida script, as this will help me understand you guys better and allow me to adapt this into my future videos. Alright. Now let's focus on this very first technique, which is based on Frida ports. So as some of you might already know that Frida works on a client server architecture model, right? On our target device, we run Frida server, and then from our machine we launch the Frida script, right? That's what we did here as well. From our machine we launched the Frida script, and on the target device we ran this Frida server, right? Here, Frida server acts as a communication channel which allows the Frida client to inject the script into the running process of the application. And once the script is injected, we can perform any kind of analysis and even manipulate the behavior of the target application. So the way this communication happens between the Frida server and client is through a dbus message. This is a special type of message which is being sent by the Frida client to the Frida server to initiate the communication and pass on the information. The default behavior of Frida server is to bind TCP port 27042. So an application can identify the presence of Frida simply by checking the availability of this specific port, right? So most likely that's what this application is trying to do, because it's trying to connect to 27042 port, right, which is the default port on which Frida listens. We can even check this port by looking at all the open TCP ports via ADB shell. Let's try that. Going back to the terminal, going to ADB shell in this new terminal, taking root permission. And in order to list out all the TCP ports which are in listening mode, we have netstat-tlnp command. This lists out all the TCP ports which are currently open. And the first TCP port which we got is 27042, which is in listening state. And if we look at the process ID or the program name, it says server. which is the name of the Frida server we have launched, right? And if I terminate this Frida server from here and check for the open ports again, you see this time we are getting 27042, but now the state is not listening, right? So let me launch Frida server again and coming back to our script. So now we know which port Frida server is listening to and how the application is trying to detect Frida using this connect function call. So in order to bypass this, we can simply try to manipulate this port argument with some other port which is not currently open in our device. So for that, let's make a condition first of all, because you only want to replace the port which is responsible for Frida, right? Let's make a if condition. If port is equal to 27042, then only we will manipulate this port. And as I explained before, the port is in a packed state, so before replacing it, here we have unpacked the port, so this time we have to pack it. So we just have to perform the reverse operation of this. So let's say I want to pack it with the port 27043 instead of 42. So for that, what we can do, let me put this packed port in a temporary variable 27043, right shift 8 followed by an AND operation with FF, 27043 AND operation with FF, left shift 8. And now put this port which is present at address +2. Now in order to read a value, we have used read U16. Similarly, to write the value at this address, we have write U16, and then the value which we want to write, which is present in this temp variable. And for our reference, let me put a console warning bypassing Frida port check. All right. So as of now, when Frida server is running and when we spawn the application using Frida, we can see that all these three detections were triggered. But after bypassing this port, let's see what do we get. We clear the terminal and launching the script again. All right, see this time that Frida detection 2 is passed now. Awesome. And in the console, don't get confused with this value because there is a small mistake we did in our script. I have put this write U16 return value into the port variable, which is now containing the address where the value is written instead of the port number itself. Let's remove it from here, and we have to read the port again and unpack it, saving it again. Let's launch it again. And now you see after bypassing Frida port check, we are getting 2743 instead of 2742, right? So our first Frida detection, which is based on port, is now bypassed. Now there is another way to bypass this detection, which is by running the Frida server on a different port. So you can try to find the command for changing the Frida port by yourself and try that. Okay, let's move on to the next Frida detection technique. But before that, let's first try to observe the behavior of the application. So after bypassing this port detection check, when we try to launch the application using Frida, it triggers these two detections, right? Frida detection 1 and Frida detection 3. Now let's kill the application and now launch the application normally from the driver. Note that this time Frida server is still running, but we have launched the application normally, not via Frida. And this time in the first detection, instead of getting the red cross mark, we are getting this green tick, which means that this detection is not being detected anymore. So based on this behavior, we can say that it's detecting something only when we are launching the application using Frida, right? So this brings us to the next detection technique, which is based on Frida artifact. So going back to the presentation, this detection is based on Frida agent. When we spawn the application or attach any Frida script to the running process, Frida injects few components into the app process memory, such as Frida agent. So if you observe from this figure, we have this target device where obviously Android runtime environment is present, and you know that the Jaguar process is the parent process of all the applications. So all the apps or program which runs on Android device are originated from this Jaguar process. And when any program is launched using Frida, a Frida agent is being injected into the runtime environment, or we can say into the app process memory. This agent is called frida-agent.so. It's basically a shared library of Frida. This agent establishes a bidirectional communication channel between Frida server and the Frida client. So in short, whenever we attach our Frida script or spawn a new process, this Frida agent.so library gets loaded into the app's process memory, which most of the application detect these days. Now there is a very simple way to detect whether this Frida agent is injected in the app's process memory or not by parsing proc self maps file. This file in Android contains information about the currently mapped memory regions and their access permissions. So let's try to have a look at this file via ADB shell. To open this maps file, first of all, we have to identify the process ID of the application which is running on the device. So this application is already running, so we have to first identify the process ID of this application. For that we can use ps-a and filter out the output with anti-frida. So this is the application which is running, right, and its process ID is 18027. Let's copy this. Now to view the contents of procmaps file, we can simply use cat command /proc, then the process ID of the application, then maps. Hit enter. And this is the content of the maps file, and it's quite overwhelming. There are few things to notice here. Here you see the memory addresses. These are the starting and the end address of the memory region where any library or any file is mapped. So in this case, let's say this libselinux.so library is being mapped into the memory starting from this memory address. Okay, and then we have the read write permissions for this library in memory. In this case, it's readable, and in the end we have the file path of the library. So the point here to notice is that if the application is spawned using Frida, then in this file you will definitely find Frida agent.so library, right? So as of now, if you remember, we have launched the application normally from the app driver. So let's clear this out and let me kill this application, and instead of launching it normally, let me launch it via Frida. All right, and let's go back to the terminal and again extract the process ID of this application. This time we are getting this process ID again using cat/proc process ID maps. Let's print out the contents and let's see whether this time we are getting Frida agent.so in the maps. As our search result says, here we have the Frida agent.so library present, right? Obviously it says deleted because that's how Frida server work. So this is the latest Frida server, and in the latest one, actually they are not keeping this Frida agent in the memory for a longer period of time. They are deleting it as soon as the script is attached, but still the references can be found from this maps file. Let's close this instance, clear the terminal. Now let's try to bypass this. For that, first we need to know how the app is opening proc self maps file. In general, to open a file we have open fopen functions, right? But as we saw in the output of our Radare, we don't have any such functions, which means that the library is using some other way to access this file. In such cases, when you don't find any interesting function in the imports and also don't find any interesting strings which could lead you to the right function, you can actually try to have a look at the instructions itself. So there is a stealthy way to call functions by using SVC instructions. These instructions are called supervisor instructions, and these instructions depends on a system call number through which it identifies which function to call along with the arguments. Don't worry if it is not clear yet. So in the beginning, if you remember, I said that there is a very specific reason why I am using Radare to disassembler, right? Now is the time to harness the power of this tool. Instead of manually searching all these SVC instructions and resolve them one by one based on the system call number, Radare 2 provides a command which does all the magic. So to search for the system call instructions, first of all we have to set the OS type using export asm.os equal to Linux. As of now, Radare 2 does not support OS type as Android, but the system call numbers are same what Linux uses, so we can set this OS type to Linux. And then to list out all the SVC instructions of set along with the function names, all we have to type is /as. There we go. We now got couple of interesting functions, right? Such as openat, read, close, lseek. All these functions are responsible for handling file operations, right? Now that we have these offsets from where these functions are being called, let's try to have a look at the disassembly to understand how these instructions work. For that, let's copy this offset and seek to this address and hit pt. Oh no, it's a very long function. Okay, so let's just disassemble this instruction itself. So here you see at this offset, we have svc0 instruction present, right? But before executing this instruction, couple of things needs to be configured, such as the system call number, which tells the operating system which function to call. So there is a system call table which contains a mapping between the system call number and the function to be executed. For ARM64, we can easily see this table by typing ARM64 Linux system call table. Click on the first result which says Chromium OS documentation. So let's click on this. There we go. Here in this particular column which says system call name, we can see the name of the function which will be called. And then the corresponding system call number is mentioned in this column, which says X8, because in ARM64 X8 register contains the system call number. So for example, in our case, we are looking at openat function, right? So we can find openat function in this column. And in this particular column, we can see the system call number, which is hex 38, right? And like I said, before executing this SVC instruction, it has to set all these registers, right? So X8 registers need to be set at hex 38 to tell SVC instruction that okay, openat function needs to be triggered. Similarly, the argument which are required by this openat function are stored in the register starting from X0. So as you see, these further columns are storing the arguments of the function in the respective registers, right? So coming back to the openat function, we see that the file descriptor is being stored in X0 register, followed by the file name, which is getting stored in X1 register, right? So the same behavior we can see here. We try to disassemble previous 4 instructions. We see that this X8 registers is getting initialized with hex 38, which is going to tell this SVC instruction which particular function to call. Similarly, if we try to disassemble more instructions, we can observe that it's initializing the X1 register with some value from the memory. As per this table, this X1 register contains the file name. So if you try to intercept this address from your FreeDIE script, you will get the file name of the function. Alright, so to intercept these system calls, we can attach the hook to all these offsets, but instead of manually copy and pasting these offsets, we can make use of another useful command provided by Radare, which is /asj. This j tells Radare to print out the output in a JSON format. So under the results, we are getting a JSON array containing the address, offsets, name, and the system call number. So we can simply copy this JSON array and paste it in our FreeDIE script so that we can iterate over this using a for loop and attach our hooks. Let's go back to the script and let's create a function with the name hook svc. Inside this function, syscall, I'm going to paste this JSON array as it is. Now to iterate over these values, I am going to make use of a for each loop. This calls dot for each. This will take a function with the argument, let's say item. Now one thing to note here is that the addresses are mentioned here in the form of integer, but to attach the hook we need to convert these addresses in hexadecimal form. So for that, let's create a variable called address and convert this address to hexadecimal form using toString function 16, and we have to prepend this value with 0x because that's how the addresses are mentioned, right? Now let's attach the interceptor using interceptor dot attach. This takes two arguments. First one is the address and the second one is the callback function, right? These are the offsets only, right? Not the actual address in memory. So to calculate the actual address, we first have to calculate the base address where the library is going to be stored in memory. So as of now, we don't know that. And in this function, we are going to take this base address as an argument. We will calculate it later. So we can simply add our offsets to this base address. Base address dot add address. Then the second argument is the callback function. So over here, actually we have different functions which are being called via system calls, and all these different functions have different system call number, right? So instead of putting several if else, let's use switch statement, and under items sys number we have the system call number, right? So in case of openAt function, the system call number is 56, and simply print the console openAt. Now we are only interested in the second argument of the openAt function because that's where the file name or the path name is defined which the application will try to access. And as we saw already, this x1 register contains the file name, right? This is what we saw from the system call table, right? Where is it? There we go. And the file name is stored in this one register, right? So to print out the value of the file name, we can use this dot context dot x1 and we can use read c string. Similarly, what's the other function we have? Read close lseek. Okay, so for read we have system call number as 63. So case 63, putting the log. So whenever read system call is executed, this log will be printed. Okay, so for read function, again let's have a look. Is here read function. First argument is file descriptor followed by a buffer. So whatever this read system call is trying to read, that is going to be stored in this character pointer buffer, okay, which is again being stored in x1 register. Print that value, we are going to use x1 register again. Similarly, the next function we have is close function, right? So for close 57, let's put the log close. Now it only takes a file descriptor, but using file descriptor we can't say manually like which file is being closed, so there is no point of printing out the file descriptor here. So let's just print this close function as a label so that we know at least, okay, when the file is being opened and when the file is being closed. Then the next function we have is lseek function 62. So the lseek function, which is at 62, takes file descriptor offset, right? So file descriptor is again of no use, but still let's just print it, which is being stored in x0 register. So let's put ft this dot context dot x0, then the offset, which is stored in x1 register, that is going to be in hexadecimal format. All right, so I think these are all the main system call functions which are listed out by radare disassembler, right? So as of now we have only defined a function where all the system call functions we have tried to intercept, but in order to call this function we first have to identify where the native library is stored in memory, which in this case is libntifrida.so, right? So for that I have explained this thing in almost all of my previous videos, but again I'm going to explain it quickly. There is a linker64 which is responsible for loading all the libraries into the memory whenever any application or process requires it. So that's the very initial point which we can target to figure out where the library is being loaded. So let's do that, but we also need to make use of dlopen function and the call constructor of linker64. So what we can do is first of all to identify the linker64 library using process dot find module by name. Here we have to pass linker64. Now note that if your device on which you are doing this is 32-bit, then only use linker, because linker64 is only available in ARM64 based devices. If you have any other device, then use linker only. All right, next we have to identify those two symbols which I have just told you, which is do dlopen and call underscore constructor. So for that I am going to use enumerate symbols API. Now this will return a list of symbols which are present in linker64. So to iterate over it, I am going to use for each loop. This will take a function, then the argument is, let's say, symbol, then the body, and here I am only looking for these two symbols. First one is to underscore dlopen. So if the symbol is do dlopen, then I am going to store the address of this symbol in do dlopen variable, which I am going to initialize null initially. Do underscore dlopen symbol dot address. Similarly, second symbol is call constructor, which I'm going to store in call constructor variable. Okay, next let's attach the interceptor on this 2dlopen function, because this is the function which is being called first by the linker to load the library into the memory. Then the address of this 2dlopen function followed by the callback function, and over here we can get the library path from x0 register. So if you see the definition for the dlopen function, you will realize that the first argument of dlopen function contains the name of the library. So that's why I'm using the x0 register. And if the library path is having libntifrida.so, then only we are going to attach interceptor on call constructor. Call constructor followed by the callback function. So when you intercept this call constructor method, you will observe that library is getting loaded multiple times, and this is done by the operating system. So we have to limit that in our script. We can have a flag, let's say lib loaded, initialize it as 0, and as soon as it initializes this library, we can check whether this library is already loaded by the linker or not. If not, then we will initialize it with 1 and we will extract out the address using process dot find module by name. The name of our library is libntifrida.so, right? Let's put this in console. libntifrida is loaded at module.base. Alright, so now we have identified where this libntifrida is loaded in memory when the application is launched, and that's where we have to call our hook svc function. And here we have to pass the base address which we can get from this module object, module.base. Let's give our script a try and see what do we get in the console. Frida, anti-Frida, hit enter. Processing instruction is not defined. This is not processing instruction, this is process. Clear, run. All right. So in the output now, we are getting a lot of read functions which are getting called via SVC instruction, right? And from the characters, it looks like it's reading proc self maps file. Interestingly, the application is reading single character at a time from the file, as we can observe from the output. As we can see that the output is quite overwhelming, and in the terminal obviously we cannot see the whole output because it's being truncated due to the buffer limitation. So let's do one thing. Let's stop this script. Okay, and let's dump this whole output into a file. For that, all we have to do is redirect the output of this command into a file. Let's say output. Enter. On the device, we can see that the application is waiting on the splash screen. So I think the whole output is being dumped into this output file by now. And here we have the output file. Let's see what do we have in this. Okay, here we can observe that after the connect function calls, it loaded this libantifrida library at this memory address, right? And immediately after that, it made a call to open@, function via SVC instruction, and it's trying to access proc self maps as we anticipated. Immediately after opening this proc self maps file, it's trying to read it character by character, which is very weird usually, but okay, whatever the case here. Now if you observe closely, it's reading this proc maps file. Here we have the starting address hyphen end address followed by read write permissions followed by the name of the library, right? That's what we observed here in the proc maps file, right? The starting address, end address, permissions followed by file name or library name. But in such a way, it would be a bit difficult to figure out which files or libraries are mapped in this proc maps file. So to better understand this, let's make some adjustments in our Frida script. So in our Frida script, what I'm going to do is, instead of printing these read characters one by one, I'm going to store them into a buffer and then print them out once next line is identified. So for that, in this hookx svc function, I am going to define a buffer, initializing it empty, and then in the read condition, instead of printing it directly, I am going to first check whether character is a new line character or not. Okay, if it's not a new line character, then I'm going to store this single character into a variable like this and then appending it into the buffer. Okay, and if it's a single line character, I'm going to print the whole buffer, and obviously we have to clear out the buffer to remove the redundancy. Now let's observe the output again. Clear. Let's clear this output file as well, save it, and let's dump the whole output again in this output file this time. As you see, it's running. There we go. We can now kill the script and observe this output file. This time we see that after open@, function, instead of printing the characters one by one, we are getting this line by line, just like what we saw from our ADB shell, right? Now it's pretty easy to figure out what all libraries are loaded or mapped. And like I mentioned, we are looking for Frida agent.so, right? So let's see whether this Frida agent.so is present or not. Okay, Frida agent.so is present. Now we just have to bypass this detection. So there are a couple of ways to bypass this. One way is to create a fake proc self maps file and replace Frida agent with some other random name. By using this approach, the detection might bypass instances where application intends to match the string Frida agent.so. Let's try to bypass this check by passing this fake maps file. But for that, first we need to dump this original proc maps file into a dummy file, and then we will replace this Frida agent.so with some random name. Okay, coming back to the terminal, make sure that the application is in running state. Okay, and from adb shell, figure out the process ID using ps-a command. Process ID in this case is 23649. Let's copy this, and I'm going to dump the output into data local temp directory. And to dump the file, I am using cat command /proc /process ID /maps and dumping it into maps file. There we go. Now before going forward, make sure that this maps file is having readable permission by all the groups. In this case, I am having read, write and executable permissions by all the groups, but in your case, if you are not getting, you can change the permission using chmod command. So to allow all the groups to read and write this, you can pass 777 to this maps file, right? I'm going to dump this maps file into SD card. So let's navigate to that directory, and to dump it, we can use cat command, then the path, which is /proc /process ID /maps, and I'm going to dump it into maps, and we have maps over here. Now the reason why I have stored it into the SD card is because we have to extract it from the SD card to our main machine in order to replace the Frida agent string with something else, and then we will move back that modified maps file to our SD card. Let's exit from this adb shell and let's go back to the directory where our application is present, which is under anti-Frida directory. And over here, using adb pull command, I am going to pull this maps file in this directory. And over here we have the maps file. Find this Frida agent. So there are 4 instances in total. We can replace this with, let's say, this whole Frida agent thing with XXXXX. Replace all. So now all the instances of Frida agent is replaced with XXXXX, right? Let's save it and go back to the terminal and push this modified maps file to the SD card. Okay, clear. Go back to adb shell, get the root permission, and now let's copy this maps file into data local temp directory, because this is the place which is accessible by all the applications. So we don't have to grant any special permissions, or we don't have to change the ownership of this file. So let's move this modified maps file into this directory. Alright, make sure that this maps file is having the desired permissions. So as we see that it's only readable and writable by these 2 groups, but not by a public group. I am going to make it readable, writable by all the groups. So I am using 777. And if we see now, this maps is readable, writable and even executable by all the groups. Okay, what we can do now is going back to the Frida script, and under this condition, when openet function is being called, we will check if this dot context dot x1 dot read c string is having self maps. If the openet function is trying to access proc self maps file, then we will replace this write utf8 string. replace this with the modified maps file which we have kept under data local temp directory, right? And for the reference, let's put a warning on the console which says bypassing proc self map. Now our script is saved. Let's clear out the terminal, launch the script again, hit enter. Now we have bypassed this first FRIDA detection as well, which is based on FRIDA agent artifact. Alright, so now we are left with the one final FRIDA detection which is present in this application, that is FRIDA detection 3. Before bypass this detection, let me explain you the theory behind this detection, which is based on memory disk comparison. Again, when you study FRIDA in detail, you will realize that FRIDA leaves a lot of footprints on the device during its runtime. So when we run FRIDA server, it injects few things into the memory and in some of the libraries such as libc.so, which is irrespective of the running process. So to explain the idea behind this detection, let's see this figure. Basically, the idea is that there is a libc library which is stored on the disk, right? And then this library is loaded into the memory by the operating system, right? Now whenever any changes is made in this library, that happens in the memory and not in the one which is stored on the disk, right? So this detection basically takes advantage of this. Whenever we run FRIDA server or we perform any sort of hooks, it manipulates certain sections of the library. So there are several sections library contains, such as headers, text section, executable section, right? So when we run FRIDA server, it injects some code into the executable section or sometimes in the text section of the library in memory, okay, and not in the one which is stored on the disk. So now whenever certain changes made in memory, so obviously the library which is present in the memory is not equal to the one which is stored on the disk. So by calculating the checksum of the library, application can detect whether it's manipulated or not. So in this case, if the application is trying to compare libc.so library with the one present in the disk, it has to first identify the memory region where libc.so is loaded in memory. For this, one way to get the memory region address is by passing proc self maps file. And as already mentioned, in proc self maps file we have initially the start and the end address followed by the file path of the library, right? So that's how proc maps file look like, right? And the program extracts this starting and end address, and once this memory region is identified, it calculates the checksum on the various sections of the library. Mostly when we attach the hook on any function which is present in libc.so, such as open or fopen function, basically the text section of the library gets modified because FRIDA injects its trampoline instructions into the epilogue of the function. And if we don't hook anything, FRIDA server injects few things in the text section of the library, due to which the original checksum gets modified when the application tries to calculate it at runtime, which lead to this detection. These type of detections are usually very hard to find statically, especially when combined with obfuscation. Luckily, this application is not so heavily obfuscated, so it would be easier for us to perform static analysis on this library, right? So to handle this situation, we need both static and dynamic analysis. So going back to the output file, and let's find libc.so here. Okay, let's do one thing. Let's reduce some of the output by commenting out this buffer. And like I mentioned, it has to compare the libc library which is present on the disk with the one which is loaded in the memory, right? So for that, at some point of time, the application has to open the library which is present on the disk using any of the functions such as openat function or open function. So since we have already hooked openat function, via our hook SVC. So by commenting out this read instruction, it would be easy for us to figure out whether the openAT function is trying to open libc library from the disk or not. Let's check that out. Again, running the script, hit enter. App is still running, and there we go. So as soon as I commented out the read system call, we can observe in the output that trying to open our fake maps file. After that, it's trying to open libc.so, which is present at this directory, right? And from here it's calling lseek function and then closing the libc.so. Then again it's opening the maps file. So from these sequence of instructions, we can assume that it's trying to calculate something from the libc.so library present in this directory and then comparing it with something which is being calculated from the maps file. So if the application is calculating the checksum on this library, it's pretty hard to intercept it dynamically in our script because the checksum logic is not depending on some inbuilt function. It's actually mathematical operations. So we have to perform some static analysis here. So to begin with the static analysis, best way is to backtrace from here. So we know that libc library is being called by openAT function, right? So let's backtrace the code from here, and for that let's make another if condition. Basically, if this x1 register contains libc.so, then we are going to print the backtrace by using thread.backtrace API, and if we pass accurate, it will try to calculate the exact offset from where this openAT function is being called using debug symbol dot from address. But in case if the library is obfuscated and stripped out, sometimes this address is not so accurate. So let me save the script now, clear, and run it again. Okay. Now as soon as the libc.so is triggered, it printed out the backtrace. So it says that this openAT function is being triggered from this offset in this library. Now instead of Radare, I am going to make use of another disassembler called Ghidra. That's because in Ghidra, easy to see the control flow graph. So I have Ghidra already configured in my environment variable. So simply by typing Ghidra run, I can launch Ghidra tool. So here we have to first import the library, which is libantifrida.so. Okay. Double click to start the analysis. Yes. Leave all the checkbox as it is and hit analyze. Once the analysis is done, we will get this disassembly. Now from our script, we got this offset, right? Before moving forward, there is one small change which we need to do. When we load any library in Ghidra, it actually start initializing it from a certain base address, which we can see by going into this memory map and clicking on this home button, and you see that the base image address is this, it's not 0. So what we can do, either you can add your offsets to this image base address in order to map it correctly in Ghidra, or you can change it and start your image base address from 0 itself. That's it. Now if we go to that address, okay, this does not look like openAT function call instructions, right? It's because there are no debug symbols and Frida Backtracer was not able to backtrace it accurately. But still, at least it pointed out to a subroutine from where openAT is being called. And it's this subroutine. So what we can do from here is we can generate the control flow graph of this routine by clicking on this display function graph. The address which we got in the backtrace is being highlighted here, which is coming from this basic block, and this basic block is coming from this subroutine, right? Okay, which is from here. So let's start analyzing it from here itself. As you can see in the first block, we have this SVC instruction which is taking hex 38, which means this is going to call openadd function, because if you remember, openadd function has system call number as hex 38, right? So that's what we can gauge from here. And so far from our dynamic analysis, we have observed that openadd function from these SVC instructions are always pointing to proc self maps file. So it's safe to assume that this openadd function is indeed trying to open proc self maps file. And if that proc self maps file is accessed successfully, then it's going to this basic block where it's trying to initialize few memory locations, followed by this block where another SVC instruction is being called, where its X8 register is getting initialized with hex 3F. Now if we go back to the system call table, 3F stands for read function. So here it's reading the file which is opened by openadd function, and as you see, it's having a kind of a loop, right? So this particular set of blocks, these are responsible for reading the proc self maps file character by character. Why I am saying it's reading character by character is because in W2 register it's taking hex 1. So if you see from the table, this count argument is actually stored in X2 register, which tells read function how much bytes to read into the buffer. So based on this, we can say that it's reading the proc maps file character by character and storing the output into this memory location using LDRB instruction. All right. Okay, moving on. So once this proc maps file is being read, then it moves to this block which is pointing to this block. Then from here it's going to this block, and over here we can observe that there are a couple of conditional blocks, right? So this looks interesting. So here it's making a comparison of W9 register with hex 6C, and if it's not equal, then it's going to this block 194C. If it's equal, then it will move on to this block. Here it's comparing W9 register with hex 69, and if it's equal, then it will move on to the next block. So it looks like it's sort of comparing some bytes, and if those sequence of bytes are equal, then it will move forward. Now let's try to convert these hex byte into character format. Its character sequence is L. Similarly, for this 69, its character sequence is I. Similarly, for the next block, the character sequence is B. Similarly, for next block, the character sequence is C. Then for hex 2E, the character sequence is dot. Then for hex 73, the character sequence is S. Then for 6F, the character sequence is O. I'm sure you are getting the pattern now. libc.so, which is libc.so. Getting some ideas? So from this flow, what we can say is that if the value which is stored in W9 register is actually equal to libc.so, then only it will take this branch, this one. Okay, right? So based on this logic, we can assume that if there is no libc.so library found in proc maps file, then most likely it will not calculate any kind of checksum. And then obviously the openadd function will not be able to open libc.so, right? So usually this is a kind of a sanity check which has to be done before opening any file. So based on this, we can try to do one thing. In our fake maps file, Let's replace all the instances of libc.so with something else. In this case, I am going to replace it with xxxx.so. Replace all. Let me close this instance of Frida, and again we have to go into ADB shell. Okay, so now we have our modified maps file present here. What we have to do is push this maps file into SD card. And now if we go into ADB shell, data local temp, taking root permission, and let's move this modified maps file back here. Now clear it out, put our device screen on top and launch the script again. Hopefully this should be enough to bypass all the checks. Waiting. Alright, so all the detections are now bypassed. This approach sometimes make device unstable because replacing proc self maps file is not an ideal way. So I will encourage you to come up with your own bypass logics for this application and let us know in the comments. I hope you gained some new insights from this video. If you appreciate our content, then please express your support by liking the video and don't forget to subscribe to the channel. Also consider joining our Telegram channel to stay connected with our community of security enthusiasts, link to which is mentioned in the description box.